All right, welcome to Unit 3, Lesson 8. So we're going to order these things from least to greatest. I'm going to stop by evaluating. 10 to the third power is the same as, get my pen working here. 10 to the third is the same as, 100 to the third is the same as 10 to the sixth, which is equal to 1 million. Square root of 100 is 10. This is a little tricky. 100 is not a power of 2. 2 to the 7th is 64. 2 to the 8th is 128. So this is someplace between 7 and 8. And then 100 is 100, obviously. And 2 to the 10th, if you multiply it out, is 1,024, which gives me an order of C, followed by B, followed by D, followed by E, followed by A. All right, the next step is a little simpler. 2 to the negative first is equal to 1/2. The opposite of the square root of 100 is negative 10. The log of 1/8 at base 2 is equal to negative 3. 0 is equal to 0. Negative 2 to the first is equal to negative 2. So for number 2, we go B, C, E, D, and A, least to greatest. Number 3, 2 to the 0 is equal to 1. Square root of 25 is 5. Log of 8 at base 2 is 3. X to the 0, where x doesn't equal 0 is 1, so that's 2 times 1, which is 2. And 2 to the negative 1/2 power is 1 over the square root of 2. All right, so in order, number 3, E, A, B, C, D. Okay, number 4. Log of 3 and base 3 is, before I just do these here, let me make a mention off to the side. The log of a to the x power in base A is equal to x. Okay? The x can, remove itself down here to the coefficient position. One of the rules of logarithms that this is equal to x log of a in base A, which makes it x times 1, which is x. So if we go through number 4 here, the first one's worth 3, second one's worth negative 2, third one's 0, fourth one's negative 1, and the last one is 4, which gives us an order of B, D, from least to greatest, B, D, C, A, E. Right? You may have seen a message flash in there. I apologize for that. All right, on this next section, I'll try to blow this graph up a little bit. The g at x function is in blue, and the f at x function is in green. When they intersect, they'll be equal. When the blue graph is above or vertically above the green graph, it would suggest that the value of the blue graph is greater than the value of the green graph. So like on the first problem, f at 0 and g at 0, notice f at 0 is and g at 0 in those locations. So the green graph is above the blue one. So f at 0 is going to be what? F is the green one. F at 0 is going to be greater than g at 0. Taking that same logic to the 2, it gets a little tricky with the 2, because when you look up here for the 2, the graphs kind of disappeared. But notice that the green graph, when they intersect right here, the green graph goes above the blue graph. The green graph is the x, so that means f at 2 is greater than g at 2. And if we switch down here to number 9, kind of going out of order, once that graph passes it, the polynomial function, so therefore there's going to be no more turns, we assume, I guess. So this f at 5 is going to be greater than g at 5 for the same reasoning as number 6. At negative 1, if you go up here, the g at x function is higher. So for number 7, g should be larger. And for the 1 and the negative 1, f at 1 is equal to 0 right here. And g at negative 1 is up above the x-axis. So g at negative 1 should be greater. All right, how many times do they intersect? Okay, so this is too hard to see. They intersect here, here, and over there. So that's a total of 3 times. How do I know? Because I just looked at the graph to see where they were hitting each other. All right, the next section is a little bit trickier. We have a polynomial. We are told one of the roots, and we have to find the factored form and the solution. So the way we're going to do this is we're going to take, first of all, what's called the rational root there, and that is that if x equals 5 is a root, then x take away 5 must be a factor. So that'll be one of my factors in here, x minus 5. And then I would long division x minus 5 into f of x, or I can use synthetic division. And in synthetic division, it's a little bit more straightforward a process. You take the root 5, and you remove the coefficients and the constant from the polynomial that you're dividing into, 1, negative 13, 52, and negative 60. And we're told that 5 is a root, which means x minus 5 is a factor. So we're going to get a 0 when we get down to this last step here, because when you divide a factor into a number, you should get a remainder of 0. So the process is you bring the 1 down. 5 times 1 is 5. That goes here. You add those together, you get negative 8. You multiply 5 times negative 8, you get negative 40. Take 52 and negative 40, you get 12. And 5 times 12 is equal to 60. And voila, we get 0. That means that the quotient is x squared minus 8x plus a 12. And if I take x squared minus 8x plus a 12 and factor it, I'm going to get x minus 2 times x minus 6, which means those are the three factors are x minus 5 times x minus 2 times x minus 6. And the other two roots are that x equals to 2 and x equals to 6. Okay. All right, same process on the next one. I'm going to take negative 6 as a root and claim that one of the factors must be x plus 6. It's x minus the root, that's a factor. All right, then I'm going to take negative 6, and by synthetic division, I'm going to take the 1, the 6, the negative 11, negative 66. Synthetic division, I'm going to be expecting a 0. Bring down the 1, it's going straight down. You multiply the 6 times the negative 1, put the answer in here, negative 6. You add those two together, you get 0. Negative 6 times 0 is 0. Negative 11 plus 0 is negative 11. Negative 6 times negative 11 is 66. And there we go, we get that nice remainder of 0, which means that my other factor, when I divide x plus 6 into this function g at x, we're going to get x squared minus 11. Now, that is not factorable if you consider that 11 is not a perfect square, but you can kind of force feed that and say that that's x plus root 11 and x minus root 11, which means the other roots are positive or negative root 11, and the other factors would be x plus 6 times x, these two here, x plus 11 times x minus 11 times x plus 6, and those would be my roots right here. Okay, so let's try the next one. It's going to be a similar process. I'll draw a line to separate these problems. This will be number 14. Do this one in green just so you can see kind of the difference. So x minus 3 is a root, so x plus 3 must be a factor. I take the root negative 3. I remove the coefficients and the constant, 1, 17, 92, and 150 on my line, expecting a 0 here. Bring down the 1. Negative 3 times 1 is negative 3. 17 and negative 3 is what, 14? Negative 3 times 14 is negative 42. 92 and negative 42 is 50. Negative 3 times 50 is negative 150. Boom. There we go. Now, this one presents a little bit of a problem because the quotient is therefore x squared plus 14x plus 50. In the previous two problems, the polynomial that we got as the quotient factored. In this case, it doesn't, but I'm going to force it to factor. And not 100% sure that everyone has seen this technique, but I'm going to go with it. I'm going to take that 50, and I'm going to erase the 50. And in place of the 50, I'm going to write plus plus 49 plus 1, which means the first three terms, x squared plus 14x plus 49, is x plus 7 squared plus 1. Now, why would I do that? Because I'm trying to force this into what would appear to be like a difference of squares. And 1 is a square, and obviously x plus 7 is a square. But it's not a difference, it's a sum. But I can force feed this thing by doing this. X plus 7 plus what essentially is going to be, let me back it up. If I make this into plus 1, I'll get my eraser to work. If I change that plus 1 into minus negative 1, now I can argue that it is a difference of two squares. But then I have to come up with what's the square root of negative 1. It happens to be I. Right? Then I come over here and I do x plus 7 minus I. So I'm factoring the difference of squares, being 1 is x plus 7 squared. Negative 1, you could argue, is not a perfect square, but the square root of negative 1 is I. So I go x plus 7 plus I, x plus 7 minus I. You could also do quadratic formula here. Maybe a little messier. So the roots are the original x plus 3, right? And that's my factored form, I should say. And my solutions are going to be negative 7 plus or minus I. If I solve each one of these for x, I'll get, in the case of this one, I'll get negative 7 minus I. In the case of that one, I'll get negative 7 plus I. All right. At the expense of the workspace for the remaining problems, I think there's one more here. Actually, I put this should be up here. But the other roots are negative 7 plus or minus I. All right. And then if I make that a little clearer, that's x plus 3. And there are my factors. Now, excuse my coughing here. On the next problem, I'm going to use this space, and then I'll come back to 16 through 19 in a second. Notice that I have x equals root 2. And I've got my polynomial there, q at x. And I could try to take the same approach again. I'll shift back to black here for number 15. And do synthetic division with root 2. That's going to be kind of messy to bring a radical through synthetic division. So what happens here now is that we have some theorems about how certain kinds of values appear as results or solutions to a polynomial equation. And in the case of when you get root 2, you have to get the conjugate pair to root 2. So in other words, irrational answers appear in conjugate pairs. So what's conjugate mean? It means if you get an a plus b as an answer, you're going to get a minus b as an answer. We saw that up here on problem 14. We got negative 7 plus I. We also got negative 7 minus I. So imaginary numbers appear in conjugate pairs when you are dealing with a polynomial function with rational coefficients. That's important. The coefficients on all of these have been rational numbers. So what I'm going to do here is I'm going to take a couple, it's going to require me to do a lot more work, unfortunately. I'm going to say, well, if x equals root 2 is one of the solutions, well, then x equals negative root 2 has to be one, which means I have to get a factor of x minus root 2 and a factor of x plus root 2. Because remember, roots imply factors, factors imply roots. Then what I'll do is I'll multiply these two together. I'll get x squared minus 2, and then I'll divide that into x to the 4th minus 6x to the 3rd, and so on. Now, in synthetic division, it works with a degree 1 divisor. So in this case, what's the rest of this thing? 3x squared plus 12x minus 10. But I have a divisor now that's second degree. So I'm doing this live, so let's hope this works out. So I'm going to take my divisor x squared, divide it into x to the 4th. X squared into x to the 4th is what? X squared, right? I then multiply x squared by x squared minus 2 and align it underneath the terms that it's alike with. So the x squared times the x squared gives me an x to the fourth. The x squared times the negative 2 gives me a negative 2x squared right there. My memory aid right now is I say draw the line and change the sign, and then what I do is I add. So when I add these, the x to the fourths cancel out. I bring down negative 6x to the third. 3 and the 2 make 5x squared. And then I bring down my 12x. This g is in my way. I don't know why. Now I repeat the process. I divide x squared into negative 6x to the third. And that's going to give me negative 6x. X squared negative 6x cubed divided by x squared is negative 6x. I multiply that sort of around the corner. Negative 6x times x squared is negative 6x cubed. Negative 6x times negative 2 is positive 12x. I draw the line. I change my signs so that I can do addition instead of subtraction. These guys cancel out. 5x squared comes down. These cancel out. I bring down the negative 10. And looks like it's going to work out nicely. X squared divided into 5x squared is plus 5. That gives me 5x squared minus 10. Draw the line, change the signs, remainder 0. So that means that my factors are x plus root 2, x minus root 2, and then x squared minus 6x plus 5. That then further factors as x minus 1 times x minus 5. So there are all my factors. My pen will work. There we go. And what are my roots? My roots are negative root 2, positive root 2, positive 1, and positive 5. Okay, so that's a tough one. All right, going back up here to the go section. I'm going to make myself a little room first and separate like that. All right, so x plus root 13 and x minus root 13, these are conjugates. So when I start doing the FOIL method, I don't have to worry about the inside and outsides because they'll be opposites. So this will be x squared minus 13. X times x is x squared, negative root 13 times positive root 13 is 13. So the next one I'm going to get x squared minus 3 root 2 times 3 root 2. And 3 root 2 times 3 root 2 is what? 3 times 3 times 2 that are known as, what, 18, I believe. 18 is correct. All right, the next one gets a little trickier. Because what I'm going to do with this is I'm going to treat this the same way I treated 16 and 17. But I'm going to look at this as x minus 4 plus 2i and x minus 4 minus 2i. So I'm just going to stick with the FOIL method where I see this as conjugates because I'm seeing this as my first part of the conjugate. And this is the second. Well, both the x minus 4s are the first. And the second ones are the minus and plus 2i. So when I multiply x minus 4 times x minus 4, which is x squared minus 6. I'm sorry, x squared. I got in there a little bit. X squared minus 8x plus 16. And then what? Minus 4i squared, right? Because 2i times 2i is 4i squared. But what's 4i squared worth? 4i squared is actually worth negative 4i squared, I should say. It's actually worth 4. Because I squared is negative 1. Negative 1 times negative 4 is 4. So when I finally get done with this problem, it's going to be, I'll put it out here, it's going to be x squared. One second. It's going to be x squared minus the 8x, but plus 20. So this is kind of the reverse of what I did in the earlier problem when I took that 50 and made it 49 plus 1. So if I wanted to factor x squared minus 8x plus 20, instead of going to the quadratic formula or something, I could think of the 20 as 16 plus 4 and kind of force feed it. All right, so the same thing here. I'm going to consider this to be x plus 5 times x plus 5, which is x squared plus 10x plus 25, minus 3i times 3i, which is 9i squared. But negative 9i squared is worth 9, so this is x squared plus 10x plus 36. And these last two, I think these last two are going to work, yeah, they're going to work pretty much the same way. So I'm going to take x minus 1 times x minus 1, which is x squared minus 2x plus 1, minus positive I times negative I, which is negative I squared. But what's that worth? Minus I squared is minus negative 1. So this is x squared minus 2x plus 2. And finally, x plus 10 times x plus 10. I'm taking the first two terms here. That's x squared plus 20x plus 100 minus I root 2 times I root 2. So that's I squared times 2. So what's that worth? That's I squared, remember, is negative 1. Remember, I root 2, just lost that part of it, times I root 2 is I squared times 2, because the I times the I is I squared. The root 2 times itself is 2. So this in here is actually worth negative 2. And so x squared plus 20x plus 100 minus negative 2 plus 102. We'll check you there. Right, that is it.